Hi everyone. So in today's session we'll continue the parts of electric drive in that power modulator. So the following are the major parts of the power modulator. One is converter, variable impedances, switching circuits. So we'll see one by one. So coming to the converters, first type of converter, AC to DC converters. So there are various ways to convert the AC to DC. If the input is fixed AC voltage, either it is single phase or three phase, by using diode bridge rectifier we can convert that fixed AC voltage to the fixed DC voltage. One is by using diode bridge rectifier or diode rectifier. Next, second one is for the same on the left side. Now the input source is, if the input source is fixed AC voltage, either single phase or three phase. For all these rectifiers, the source is that kind of source. So by using fully controlled rectifier, second one, by using fully controlled thyristor rectifier, we can get the variable DC voltage. As thyristors are there, control switches are there. By controlling that switches, in the fully controlled thyristor rectifier, we can get the variable DC voltage. Next one is, third one is half controlled thyristor rectifier. So here also again control switches are there, that is thyristor, but it is half controlled thyristor rectifier. By this also we can get the variable DC voltage. The first one is diode bridge rectifier, right? By that we got only fixed DC voltage. But by using the diode bridge rectifier, also we can get the variable DC voltage. If you see the fourth one, last one, for the same fixed AC voltage either single phase or three phase, by using transformers with tappings. If you provide the transformer with tappings, for different tappings, we'll get the different AC level voltage. That's what variable AC voltage. By using that AC voltage and keeping the diode bridge rectifier, you'll get the variable DC voltage. Unlike the first one, fourth one is we have used the transformers to get the variable AC voltage. From that variable AC voltage, we are getting the variable DC voltage. That means input is fixed, output is variable for the fourth one, but in between the transformer and diode bridge rectifier, you are getting the variable AC voltage. Because of that, by using diode bridge rectifier, we are getting that variable DC voltage. And next one, fifth one is, again if you use diode bridge rectifier, you can get the fixed DC voltage. But to get the variable DC voltage, output of the diode bridge rectifier is connected with the chopper or DC to DC converter. From that we can get the variable DC voltage. So finally our objective is we need to get that variable DC voltage. To get that variable DC voltage, what are the possible ways from the fixed AC voltage? That's what we are seeing here. And the sixth one is a rectifier with self-commutated switches. So rectifier with self-commutated, earlier with thyristors means that is not self-commutated device, right? So that is naturally commutated device. But here the rectifier with self-commutated device like MOSFET or IGBT you can use, and we can get the variable DC voltage. And seventh one is from the fixed AC voltage, just you connect that to the AC motor. So AC motor will run the shaft, that shaft is connected to the DC generator. So AC motor will be coupled with the DC generator. AC motor will take the supply from AC voltage, fixed AC voltage, and that will run the shaft, that electrical to mechanical energy. That mechanical energy is input to the DC generator to get the variable DC voltage. This is also one way to get the variable DC voltage. And eighth one is from the AC motor is connected to the AC voltage. Now AC motor shaft is connected to the alternator. Instead of earlier DC generator directly, here we are connecting the AC motor and AC generator. That is nothing but alternator, shaft coupled AC motor and alternator used. From AC voltage, AC motor will run, and mechanical energy will be given to the alternator through the shaft, and that will give the AC voltage, right? Alternator will give the AC voltage, controlled AC voltage. That voltage is connected to the diode bridge rectifier, and so that controlled AC voltage will get the controlled DC voltage or variable DC voltage at the output of the diode bridge rectifier. And the ninth one is again from the AC voltage by using magnetic amplifier. So this magnetic amplifier also will supply the or will give the variable magnified electric signals at the output of the amplifier, and that is connected to the diode bridge rectifier, so that we will get the variable DC voltage. And the last one is 10th one from the fixed AC voltage by using amplitude also to convert the AC to DC will use, and here directly we are getting that variable DC voltage from the fixed AC voltage. So all these are the possible ways to get the variable DC voltage from the fixed AC voltage. So in this way we can use any one of the method to get that variable DC voltage, but we will see that economical aspects, size, cost, efficiency, all those things we'll see, and we'll choose that proper converter, AC to DC converter method in the drives. And second type of converter is AC voltage controllers or AC regulators. So here AC voltage controllers means to convert the AC voltage to AC voltage, that is fixed AC voltage to variable AC voltage. If you see the first one, for all these AC voltage controllers, input is fixed AC voltage, either single phase or three phase, and by using the first type of converter, that is nothing but auto transformer of fixed turns ratio. By using this auto transformer of fixed turns ratio, we'll get the low AC voltage and fixed AC voltage. For auto transformer, when you are adjusting the tappings or turns ratio, you will get the different voltages. From the input to output, voltage will be low. That means input, if it is 230 volt single phase auto transformer, means single phase auto transformer will give 230 as an input voltage. Output will get either 230 or less than 230. From 0 to 230 volts we can get by adjusting the turns ratio of the auto transformer. That's what low and fixed AC voltage. And second one is again from the same fixed AC voltage as an input. Now the transformer is provided with the tappings. If you are providing with tappings, then we'll get the, for different tappings we'll get the different voltage. That's what we'll get the variable AC voltage by with that transformer with tappings. And third one is for the same fixed AC voltage, if you use the thyristor voltage controllers, it is nothing but AC voltage controllers, thyristor switches will use. By controlling that switches, we can get the variable AC voltage. For different firing angles, we can get the different AC voltage. Either it is single phase or three phase. By controlling the thyristors in the voltage controllers, we can get the variable AC voltage, the third one. And coming to the fourth one, again fourth one, magnetic amplifier means just to amplify that electrical signals, we'll use that magnetic amplifier for the fixed AC voltage as an input. That amplified voltage will get it at the output as a variable AC voltage. Among all these things, few may have drawbacks and few may have advantage. So, but most of the time we'll use the third one. Anyway, we'll see. To get the variable AC voltage of the same frequency from a source of fixed AC voltage. From the fixed AC voltage, if you want to get the variable AC voltage of same frequency, first one is avoided due to the sliding contacts. Here, what is first one? First one is auto transformer. So that auto transformer is avoided due to that sliding contacts. So that the efficiency will be poor. Mechanical involvement is there, right? And the second one is transformer with tappings, right? Second way of conversion is transformer with tappings. The control is exercised by a mechanical force with discrete steps of voltage. So here second one is the transformer with tappings. So this involves the mechanical force as well as the discrete steps. For different tappings, different voltage means discrete steps of output variable AC voltage will get it. That's why this is also avoided to get that high efficiency, and in smooth control of drives will avoid these things. And third one is thyristor controlled thyristor AC voltage controllers. Third one, right? So for the thyristor AC voltage controller, that gives the stepless control of the output voltage because of the controlling switches, power semiconductor devices. We can achieve that stepless control of the output voltage, and it can be obtained by controlling the firing angle of the converter. That is nothing but firing angle of the converter switches, that is thyristors, by low power signals from a control circuit or control unit. Hence the output voltage and the source current have harmonics and power factor is poor at low output voltages. Even though thyristor AC voltage controller will give the smooth AC voltage controlling, but it has some drawbacks like harmonics and low power factor or poor power factor. Because of the output voltage and source current have the harmonics and power factor is poor at low output voltage because we are controlling the input voltage. So your output voltage, you are getting AC voltage by allowing the input voltage with switches control. We are restricting the input voltage by turning on and turning off the switches that will control the input voltage as well as the current, source current. That is nothing but output voltage and source current. That's why that because of that source current controlling, harmonics will be more. Hence the power factor is poor at low output voltages. And fourth one is magnetic amplifier, and this is also avoided because of the high cost, as it involves the magnetic material, high cost, weight and volume with poor efficiency. Because of these reasons, the magnetic amplifier is avoided. Among all these things, thyristor AC voltage controller is better one to get that smooth voltage control at higher output voltages. Anyway, low output voltages we face few problems, but we can use the AC voltage controller at higher output voltages. And third one is DC to DC converters or choppers. Here again DC to DC converter is designed with the power semiconductor device. From the fixed DC voltage where the supply is with DC type, from there if you need to get that variable DC voltage, we need to go with the DC to DC converter or chopper. If your supply voltage is DC voltage, then we need to go with the DC to DC converter to get that variable DC voltage. And this next one is inverter. Here to get that variable frequency as a supply from a DC supply. That means if your supply is DC again, and from that we need to get the AC voltage and with variable frequency. We need to get the AC sub DC to AC with variable frequency. To get that, we'll go with the stepped waveform inverter can be designed, or stepped inverter can be designed to behave as a voltage source or current source. Accordingly, they are known as voltage source inverter or current source inverter. Okay. So either voltage source or current source inverter can be designed again by using the power semiconductor device in the inverters. So for example, if again your supply is DC voltage, fixed DC voltage, by using that stepped wave semiconductor inverter or stepped wave inverter, we can get the variable frequency, fixed AC voltage or current. From that, even 180 degrees control, 120 degrees control mode, so those things we'll see during that inverter control mode or AC drives. In the AC drives we'll see. And next type is PWM inverters. Again for that fixed DC voltage, if you want to get the variable frequency and fixed AC voltage or current, we can use the PWM pulses. So that is nothing but pulse width modulated inverters. By that we can get the required frequency. Even we can control, in both the cases we can control the voltage also. Next one is cycloconverters. Cycloconverter is used to convert the fixed voltage and frequency of AC. That is nothing but AC fixed voltage and frequency is converted into the AC variable voltage and variable frequency. That's what cycloconverter do. So here fixed AC voltage and with fixed frequency need to be converted to the variable voltage and variable frequency, means we will use the cycloconverter. The output frequency is restricted to the 40% of the supply frequency. Here output frequency is restricted to the 40% of the supply frequency in order to keep that harmonics in the output voltage and the source current within the acceptable limits. To keep that harmonics within the acceptable limits, we need to go for the certain ratio of frequency control only, that is it is restricted to the 40% of the supply frequency only. So the other type of power modulator is variable, the part of the power modulator is variable impedances. Here variable resistors are commonly used for the control of the low cost DC and AC drives, and also need for dynamic braking of the drives. So these variable resistors were required to control the low cost AC and DC drives, and in dynamic braking also we'll use that resistor or rheostat. But the problem with this rheostats is it consumes the power. The power is going to be wasted as a heat in that variable resistors, and it will not give the smooth control. We need to adjust that variable rheostat or variable resistor knob continuously. Instead of that, we can go for the stepless variation of resistance can be obtained using the semiconductor switch in parallel with a fixed resistance. Instead of using the variable rheostat or variable resistor or rheostat, we can use the fixed resistance and we can connect one power semiconductor switch, controlling switch across the fixed resistance, so that by controlling that switch we can get the variable resistance. Anyway, by turning on the switch, your resistance is 0 because switch is connected across the resistance, means by turning on the switch your resistance is 0 because parallel connected. Turning on the switch means simply it is short circuited. By turning off the switch means your complete resistance will be across that points, parallel path. Full resistance will come. So by turning on and turning off by using the PWM switches or IGBT switch, if you are controlling that switch by turning on and turning off, you can get the average resistance that can be at any level from the 0 to full resistance. So that's what we can do for the stepless variation of resistance. Hint again, in higher power applications, liquid rheostats known as slip regulators are employed to get the stepless variation of resistance. Generally, in higher power applications, if you are using that variable rheostat, it will consume more power. That power is wasted, and it will be as a heat. So for that, we'll use a slip regulators to get that stepless variation of resistance. Inductors usually in two steps, one is full, another one is zero, are employed for limiting the starting current of the AC motor. Anyway, to limit the starting current, if you connect one inductor, it will not allow the sudden change in current. That's what it means. Old drives may also employ saturable reactors for the control of induction motor. Saturable reactors or inductors are connected to limit the induction motor starting currents. In saturable reactors, reactance is controlled steplessly by controlling the DC current of the control winding. So that's what we will do with this variable impedances. And the next one is switching circuits. The switching operations are required to achieve any one of the following. Power modulator involves or it consists switching circuits also. So the switching circuit is very important, because of the switching circuits only we can get the required operation at the output of the drive. So the following are the switching operations. One is charging the motor connections to change its quadrant of operation. So that is changing the motor connections to change its quadrant of operation. Changing the motor connections means by changing the motor connections with the turning on and turning off the switches, we can enter into the different quadrants. That may be forward motoring to forward braking, first quadrant to second quadrant, or reverse motoring to reverse braking. That may be from third quadrant to fourth quadrant. So if you want to change that quadrant of operation, either motoring to braking or braking to motoring, we need to change the motor connections by using these switching circuits. But the switching circuits will send the proper pulses to that switches to turn on or turn off to give the required quadrant of operation. Second one is for changing the motor circuit parameters in the discrete steps. So that's what circuit parameters will change again by giving the proper pulses to the switches in the converter or power modulator. For automatic starting and braking control, so nowadays everything is automatic starting and braking control, just by with some switch, by one switch, the pulses we need to send it properly for the automatic starting and braking with the speed adjustment. Self-driven cars have come, even without having that clutch also. Automatic, based on the speed itself, it will adjust this based on the speed, it will change its gears. So all this is possible by proper switching circuits. For operating the motors and drives according to a predetermined sequence. Predetermined sequence means if we want to allow the motor from one state to another state after some extent or after some time, or at particular voltage level or at particular power level. So that is predetermined sequence. During that time, your switching circuit will send the signals to the switches to turn on or turn off, to change its quadrant of operation, or to change the state from one state to another state, to provide the interlocking to prevent the mal operation. So interlocking, to provide that interlocking to prevent that mal operation means where the interlocking is required, otherwise the equipment may damage. So in that case, the firing sequence should be uh, given in a proper way. If we, because of malfunctioning of the devices, because of the improper firing sequence, your devices will malfunction. So instead of turning on at 1 second, if it turns on at 0.9 second, both the switches in the same leg of the converter will turn on and it will completely short circuit that devices. So such malfunctions need to be avoided by giving the proper switching circuits. To disconnect the motor when abnormal operating conditions occur. Whenever such abnormal conditions occur, short circuit or open circuit of the devices, in that case your complete system need to be protected. For that we need to give one signal through the switching circuits. And switching operations in motors power circuit are carried out by high power electromagnetic relays known as contactors. Nowadays even in generation systems also, that electromagnetic relays at high power will be used to switch that operations from one state to other state. Even the thyristor switch is also employed to get that required operations. And thyristor switches have the disadvantage that they cannot provide the perfect isolation between the source and motor circuit. So that is a problem with the thyristor switches. Thyristor switches do not provide that perfect isolation between the source and motor circuit. For that again we need the isolator. That isolation circuit is required. That involves again cost. Otherwise thyristor switch is a good switch. It gives better performance, but that isolation problem, because of that isolation problem, it has some restrictions. And solid state relays have replaced low power electromagnetic relays almost in all applications. So by using these solid state switches means we can control smoothly. Only the thing is that you need to give the proper switching sequence from the switching controls circuit. That's why all these low power electromagnetic relays have been replaced by using this solid state relays. For the implementation of complicated sequencing and interlocking operations, the programmable logic controllers PLCs are employed with the proper programming. So this is all about the power modulator. Thank you all.